Let's look at another problem where we have to construct the growth function from given information. So while working for a bacteria colony, Trey notices that his initial colony of 294 quadruples every 40 minutes. A, find the growth model for the bacteria colony, round to 6 decimal places, and B, how many bacteria are there after 1 hour? So this is different from the radioactive decay in that I'm actually given a starting amount. So with the decay, I was just told the half-life, which I was able to infer that no matter what I start with, after 4 days, it goes to half. This one, I need, so here's my model, right? P of t is P naught a to the t. Okay, so I'm going to need to know P of t for some amount of time. I need an initial and I need a time. And I do have all of these, right? I have that after 40 minutes, the initial of 294 has increased to whatever 294 times 4 is. 1,176. So that means A is my question mark, and I'm going to be able to solve for A. All right. So we get 1176 equals 294 times A to the 40. So divide both sides by 294. And then take a 40th root of each side. So 1176 over 294. Now for punching this into a calculator, I absolutely would leave this as 1176 over 294. Don't truncate this before you have to. So if I type this on a calculator, here's what I would write. 2 ways to do it, right? You can either use the reciprocal or the fractional power, or you can do the root button. This one does have a root, okay. So calculator. You can either write this is probably the easiest. 1176 divided by 294 caret parenthesis 1 divided by 40. Right? So here it is on the yellow calculator. Parenthesis 1176 divided by 294 to the power 1 divided by 40. You need to include the 1 divided by 40 in the parenthesis. All right, equals, so I get 1.035264924. Oops. So that's 1.03526. There's my 265. 62. There we go. All right, so that's 6 decimal places. All right, so what you get is the function P of t is 294 times 1.03526 to the t. Now if you use the root button instead, that's fine. On my Casio, which I really like this calculator a lot, because it has a root button and it looks exactly like this. So I can type exactly this thing. So 40.1176 divided by 294. And that's what I have written on my paper. And I get the same thing as I did on the yellow calculator. All right, for B, how many bacteria are in the colony after 1 minute? Or sorry, 1 hour. Oh, by the way, let's remind ourselves, in goes something, out comes something. So find the growth model. T is time, and we did 40, right? 40 what? Minutes. So in goes some number of minutes, out comes number of bacteria. In goes minutes, out comes bacteria. So on B, when you're asked how many bacteria after 1 hour, that's not 1, but 60 minutes. So we actually want P at 60, which is 294 times 1.035265 raised to the 60th power. And that you can enter exactly like it looks. Again, if you have the caret button on your calculator, then use the caret. So 294 times 1.035265 to the 40th power. So, oh, I'm sorry, 60th power. Which, hey, look at that. 1176 after 40 minutes, which is exactly what we said when we constructed it. Okay. 60 minutes. All right, 2352. It says round to, it doesn't say, so we'll round to the whole, nearest whole bacteria. Which is 2352 bacteria. So the only difference between this problem and the radioactive decay problem is I tell you how much you start with, and you have to infer what that means about having quadrupled. I could have just as easily said, Trey notices that his colony quadruples every 40 minutes. And then you'd be back to doing a problem like the decay one where you just pick a starting amount and you know that after 40 minutes it's 4 times whatever you started with. So, all right, so that is this problem. All of the growth and decay models basically work like one of these that I have done. These with the multiple parts are definitely the hardest. If you can do this one in the decay, then you should be able to do just about any of the growth decay models.